Can you hear me? It has been a glorious time to be alive and doing research in theoretical physics. Our picture of the universe has changed a great deal in the last 50 years, and I'm happy if I have made a small contribution. The fact that we humans, who are ourselves mere collections of fundamental particles of nature, have been able to come this close to an understanding of the laws governing us and our universe is a great triumph. I want to share my excitement and enthusiasm about this quest. So remember to look up at the stars and not down at your feet. Try to make sense of what you see, and wonder about what makes the universe exist. Be curious. And however difficult life may seem, there is always something you can do, and succeed at. It matters that you don't just give up. Thank you for listening.
Hello. On Wednesday, March the 14th, the world was shaken by the death of one of our greatest scientists, Professor Stephen Hawking. So this week's programme is dedicated to celebrating his life and his work.
In the next hour, we'll be exploring his scientific successes and hearing from the people he's inspired. I'm Georgia Mills.
I'm Chris Smith, and this is The Naked Scientists.
The Naked Scientists podcast is powered by ukfast.co.uk.
With us this week are Professor Lord Martin Rees. He's the Astronomer Royal, and he's going to help us to get to grips with Stephen Hawking's earliest work.
Cosmologists Andrew Pontzen and Claudia Duran will be talking to them about how Stephen Hawking explored the mysteries of black holes and the phenomenon that now bears his name.
The director of Intel's Anticipatory Computing Lab, Lama Nachman, is also here. They played a key role in Stephen's speech technology that communicated his work and his wisdom to the world. And
Professor Jerry Gilmore, also a cosmologist, will be discussing the impact Professor Hawking had on science and our understanding of it.
And neurologist Jameen Sridharan from the Babraham Institute in Cambridge tells us more about motor neuron disease, the affliction that Stephen Hawking had during his lifetime.
Welcome everyone, thanks for joining us. So let's start with a look at the beginning of Professor Stephen Hawking's career. He started out as an undergraduate at Oxford University in 1959 and then made his way over to Cambridge in the early 60s to start a PhD. He subsequently became a fellow of Gonville and Caius College, a place he described as a constant thread running through his life. I went to meet the master of Caius, Professor Sir Alan Furst, to find out more about his time there.
Oh, he was larger than life. You know, his presence was felt all the time, but we were very, very proud of him. And he clearly loved the college as well. Stephen first came here in 1965 as a research fellow. A research fellowship is a very prestigious award for outstanding young people to study and do research.
And when did you first encounter him?
I first encountered him in 1965 as well, because I started that year as a graduate student. In those days, as today, students would dine in college, as would the faculty, or dons as we call them. The dons would sit at high table, we would be slightly lower down. And I remember very well seeing Stephen hobble onto high table with the aid of a stick. We knew in those days that he was a very special person because of his brilliance. What we didn't know, and didn't learn until a little later, that he was meant to live only another 2 years. I went away from Cambridge and came back in 1988 as a fellow of this college and met up with Stephen again, and I even took part in a conference with him on the origins of life and the origins of the universe, and I spoke more about life and he obviously spoke about the universe. But I've got to know him a lot more since I became master, and I would entertain him on high table, this time as master, rather than look at him as a student. He would be wheeled in by his carers. He really enjoyed coming into college, he liked seeing people, he liked being with the students, and the students loved Stephen's coming in.
So what was he like as a character? How did people know him?
He was fun. He clearly enjoyed himself, and he clearly wanted everybody else to enjoy themselves. And he was never put out by anything he was asked to do. He was perfectly happy to pose with selfies. He was happy to help with the college to raise money. He would inspire students. He would see people. And he had a mischievous sense of humour.
I've heard rumours that he liked to host parties as well.
Oh, he certainly did. I was only ever invited to one of them. It was about 6 months after I came master. And it was a fancy dress one. Well, I didn't realise it was fancy dress, but his intimate guests did. And he was dressed up as Neptune with a trident.
And is it here he hosted his infamous time travellers party as well?
Yes, it was. It was in his room in Keys that he waited for the time traveller to come back and have tea with him. I gather it didn't work out.
Well, who knows? Maybe the time travellers just got the date wrong.
On the other hand, they might just be trying to keep us guessing. Stephen Hawking's earliest work in the 1960s coincided with a very exciting period in astronomy and cosmology, and that was the time when evidence first began to emerge for black holes and the Big Bang. Professor Lord Martin Rees is the Astronomer Royal. He was also a contemporary of Stephen Hawking in Cambridge. Welcome, Martin. What did he study when he first came to Cambridge? What was the problem he set out to solve?
Well, I knew him from that time. I started 2 years after him, and he was very lucky, as I was, to have a good supervisor called Professor Dennis Sharma. And Dennis Sharma had a good feel for what was important. And he gave Stephen some good advice, which was to go to London to hear lectures by Professor Roger Penrose, who was developing new ideas of understanding black holes. And Stephen took this idea and ran with it, as it were, and his early work was on applying Penrose's ideas to show that inside a black hole a so-called singularity developed, where everything would go infinite and it was a signal for new physics. And he also, at that time, got some new ideas about the nature of black holes, because he and others showed that any black hole that existed in the universe would be described by a very standard equation. And this was a very big idea, and especially important because this was a time when people were starting to observe evidence for black holes, objects called quasars, objects which outshone an entire galaxy even though they were no bigger than a star, discovered in 1963. And it was realised later that they probably involved big black holes.
So people did have an insight into the existence of black holes, but they had not really any way of grappling with how they behaved or what their evolution was likely to be. And it took Stephen Hawking to apply the equations of Roger Penrose to then work out how we could grapple cognitively with what these entities might be.
That's right. The evidence that they actually existed really came up rather gradually after 1970. That most people believed black holes existed. But Stephen was one of those who really told us what black holes were like, and that they were standardized objects. And George Ellis and Stephen Hawking wrote the classic textbook on this subject in the early 1970s.
You said that at the centre of a black hole is this concept of a singularity. What's that, and why was that such a breakthrough for Stephen Hawking to begin to get to grips with?
Well, to explain why this is important, if you imagine something which is completely spherical and collapses, then no one's surprised that it goes to a point. But the important result of Penrose and Hawking's work was that even if something collapses in an irregular way, then once it gets past a point of no return, it will actually form a singularity where things go infinite. Now, of course, that is just what the theory says. And when we have a singularity in physics, that just means we have a signal that the physics we have is incomplete and something else comes in. So that was the first indication that places existed in the universe where we would have to modify Einstein's theory and perhaps bring in quantum theory as well.
One of the other guests here this week is Andrew Pontzen, who I think famously said on this programme, Andrew, that you have to be very careful with theoretical physics because you can prove anything is right. Is that one of the issues with Stephen's work, in the sense that you could prove on paper that something might be happening, but actually having evidence for it happening and observation is a very different thing, and that was what we had to wait for?
Well, it's been harder because we've had pretty good evidence that Many objects like quasars are powered by gas swirling down into something which is like a black hole, something with a deep gravity potential. But whether that was exactly the kind of black hole which Einstein's theory predicted, according to the work of Hawking and others, that took a long time. And even now, it's not completely clear. There is some evidence that those models do work quite well. But the most important proof that black holes did behave in Einstein's way was only just a couple of years ago when gravitational waves were found. This was a phenomenon where two black holes were spiraling together into one, and they shake around and eventually settle down into a single black hole. And in that process, they emit ripples in space, as it were, gravitational waves. And these were detected for the first time just 2 years ago. And this was a really strong confirmation of Einstein's theory in a context where it's very important. I mean, in most of astronomy, Einstein's theory is just a small correction to Newton's theory, which is good enough in most purposes. But here we have phenomena that Newton couldn't explain at all, and Einstein's theory seemed to be borne out, and the black hole seemed to behave in a way that was consistent with what people had discovered, partly due to Stephen Hawking's work.
What did Stephen Hawking make of the LIGO experiments that detected gravitational waves? Did you talk to him about that? What was his reaction?
He was delighted because this was an observation which could in principle have refuted one of his key ideas. He had shown that a black hole had a surface area that could never decrease, and if two black holes merged, then the black hole that resulted would have to have an area which is bigger than the sum of the first two. Now, that could have been refuted by this experiment if it had found that the merged black hole was radiating at a high frequency applying a low mass, and it wasn't. And he was happy that that was the nearest that astronomers had got to actually testing one of his key ideas.
Martin, thank you very much. That's Martin Rees, the Astronomer Royal.
In his early 20s, Professor Hawking was diagnosed with a rare neurological condition called motor neurone disease, or MND. He was unusually young to have developed the condition, which usually affects people in their 60s and 70s and is often fatal within a few years. Yet, despite his diagnosis, Stephen Hawking managed to survive and cope with the disease to reach the age of 76. Jameen Sridharan studies motor neurone disease at the Babraham Institute in Cambridge and King's College London. Welcome to the programme. So can you tell us what actually is motor neurone disease?
Hello. Motor neurone disease is a destructive degenerative disease of the brain and the spinal cord. It affects predominantly the motor nerves, which is why it causes paralysis. People are unable to breathe or to move or to swallow. So it's quite a debilitating disease, and there's no cure at the moment.
Do we have any idea what causes it?
In about 10% of cases, there are genes that we know of that cause the disease. At the moment, we're trying to work out how these genes actually cause damage to nerve cells. In the other 90%, it's not very clear what causes the disease. These patients tend to be completely normal, with no previous family history, no previous ill health.
So what actually happens to someone with this condition?
So those nerves supply muscles that are important for swallowing, for speech, for breathing and for movement. So all of those processes can suffer as a consequence, and different people will have different symptoms. So if it affects the muscles of the legs, difficulty walking, and muscles of the hands, difficulty turning handles or turning keys, for example. And if it affects the bulbar muscles, as we call it can cause problems speaking and swallowing. Patients can often have problems thinking, changes in their behavior and changes in their language as well. Although in general, one of the most striking things about MND is that patients can feel and they can see, and they still have bowel and bladder function, and yet for some reason it's just the motor nerves that seem to die.
Do we know what's killing them?
Yeah, this is a very important question. I mean, one of the things that we might think about is the size of a motor nerve. If you think of an individual who's maybe 2 meters tall, a motor nerve may be a meter in length. It's one of the largest cells in the body. The upper motor neuron has to go from the brain down to the spinal cord, and then from the spinal cord out to the big toe. So that's a very big cell, and you've got to somehow maintain that cell for your entire lifetime, and that's not an easy thing to do.
Oh, I see. So these sort of the cables within you that you need to be intact. If they break, that's it.
Yeah, I mean, they can regenerate. So if you were to sustain an injury to your arm, for example, nerves can grow back. In the case of motor neuron disease, they don't grow back quite so well.
And you mentioned there's no cure. Is there any way to treat this?
So there's one drug that's being used at the moment in the UK called Riluzole, and most of our patients take that drug. There are other drugs in development around the world that are licensed in other countries. They have a relatively small effect on the disease progress. So at the moment we're working very hard to try and develop therapies that are really effective and going to slow down the disease process in a more effective way
And so this disease is something you look into in your lab. So how are you investigating it?
So we use a number of different tools. Most recently, I've done a fly model. And recently, we've done a mouse model. And this is a brand new model of motor neuron disease. And it gets dementia, which is quite interesting, because we know that in humans, MND and frontotemporal dementia overlap quite a lot. And that's something that's relatively underappreciated, but increasingly recognized now. So the mouse is completely different to other mouse models in that we haven't tried to make the animal deliberately very sick, which is the general approach. What we've done is replicated the human condition. We've made a 1 in 3 billion genetic change, which makes it look like a human basically, because the mouse has the same protein as we have. And we've found in the brains of these animals that they have changes in certain kinds of nerve cells that you wouldn't normally have thought would be linked with motor neuron disease.
Okay, so when scientists examine diseases, what they often do is give this disease to a mouse. We call it a model. And what you've done is made it much more similar to how it expresses in humans rather than how it is in mice.
Yeah.
So what has this told you?
So what it's told us, the most important thing, is that the protein normally, through a kind of very intricate homeostatic mechanism, regulates its own expression. In this mouse, we see that the protein level is actually higher than normal. So we haven't tried to increase the protein level, but the mutation results in the protein losing its ability to regulate. And that causes a whole chain reaction, because what it normally does is it regulates other genes' expression. And all of that has gone wrong. And what we find is that the more of this protein that you have, the more other gene expressions will go wrong. One of those genes happens to be a gene that encodes tau, which is a protein that's linked to Alzheimer's disease, which has never been discovered before.
Okay, so it sounds like you're putting pieces of the jigsaw together here. Does this mean now we know that protein goes wrong, we can target it with a drug?
What we're trying to do now is to work out whether this is relevant to humans. But we think it is. The reason is that this protein is highly conserved, which means that it's exactly the same pretty much as in humans. So we're trying to work with human stem cells now to kind of confirm that finding. And if that's the case, then it's something that we can target. It's complicated because the protein TDP-43, too much of it is bad, too little of it is bad as well. So we can't just find ways of reducing the expression. We have to be very careful about how we balance that level of expression. And we have to try and do that specifically within the nervous system. The protein is present all over the body, but it seems to be the brain and the spinal cord that are particularly vulnerable.
Well, I wish you luck with it. Thank you very much. That's Dr. Jameen Sridharan from the Babraham Institute at Cambridge University and King's College London. If you'd like to hear more about that study, we are releasing a small podcast about it on our specials feed. That's nakedscientist.com/specials.
Now, despite his diagnosis and its grim prognosis, which might have seen him survive for only a few more years as far as he knew at the time, Professor Hawking nonetheless continued with his research. And a lot of this was exploring the intricacies, as we were hearing from Martin Rees, of black holes and how they worked. Well, we're joined now by cosmologist Andrew Pontzen. He's at University College London. His other claim to fame is he wrote some of the appendices to the latest edition of Stephen Hawking's very famous book, A Brief History of Time. We'll hear a bit more about that later on in the programme. But first, Andrew, welcome. Why would black holes have been tempting or tantalising as a problem for the young Stephen Hawking in the first place?
Thanks. Well, as we heard from Martin Rees earlier on, he was particularly interested in black holes for a variety of reasons. But I think once you start getting into them, they remain tantalizing because they are the most extreme objects that we can really think of in physics. You know, they are the objects where gravity has gone slightly crazy. To actually understand what makes them tick is, I think, something that many cosmologists would like to do. And gravity is a very mysterious force, actually. It really doesn't behave in the way that the other forces that we know about behave. And so understanding a black hole is about drilling down, understanding gravity, and it sort of becomes a sort of fantastic playground almost for theoretical ideas.
I like that analogy. Now, one of the things that Stephen Hawking did do was to highlight some of the potential sort of energy balance issues concerned with black holes. Tell us a bit about that.
Well, a black hole has something like a surface area. You can think of it as a sphere sitting in space. And so you could go and, in principle, you could measure the surface area of that sphere. And he showed that if you take two black holes and throw them together, then in the end, you'll end up with a black hole whose total area that you end up with has got to be greater than the area of the two black holes that you started off with summed. So it's a sort of thing where you add two things together and you know that total area can never go downwards.
Sounds like the national debt.
It is a bit like national debt, but in fact it's also a bit like something else we know about in physics. And another physicist, Jacob Bekenstein, pointed out that this is very much like what we call entropy. Entropy is a sort of measure of disorder in the universe. And there's a very fundamental law in what we call thermodynamics, which states that entropy also must always increase. That is, if you're summing all the entropy in the universe, then the overall entropy of the universe increases. In other words, the universe is getting more and more and more messy as time goes on. And so Jacob Bekenstein pointed out, actually, this is a very close connection, and went as far as actually suggesting that perhaps that means that black holes themselves, what we're seeing in terms of this ever-increasing area, is in fact another manifestation of that idea that entropy in the universe also has to increase.
But equally, the other, I think, striking thing that now bears Stephen Hawking's name is the whole idea that black holes don't just draw stuff in, they do give things off. There is this Hawking radiation, isn't there?
Yes, so this was Stephen Hawking's next big contribution, really. He took this idea of Jacob Bekenstein's that black holes have entropy, and he says, well, if that's true, then they must be taking part in other processes in physics. Entropy in physics we normally associate with disorder. We normally associate it with having lots of little particles of matter or chunks of energy that are getting themselves into a complete mess and getting into disorder. So he suggested that if black holes possess entropy, they must also be able to generate disordered particles of radiation. So it was a very strange conclusion to come to.
So in essence then, we've got this material which is leaking out of a black hole, for want of a better phrase. This is slightly paradoxical because everyone thought black holes don't leak anything. They're black for a reason. They're soaking up everything, including light. So what is the stuff that effectively is coming out, and at what sort of rate, what sort of volume?
You're absolutely right that, of course, the famous thing about a black hole is supposed to be that it's black, that nothing can ever come out of a black hole, including light. This is an example of what we call a quantum correction, that although in the sort of classical picture of physics, a black hole would be completely black, when you put in quantum mechanics, you get a very, very small correction to that picture. And the kind of rate we're talking about stuff leaking back out of a black hole is incredibly slow. The way I like to think about this is, imagine the sun. And I want you to imagine that the sun gets dimmer and dimmer and dimmer and dimmer until it's about as bright as a torch. Right? That's an enormous factor. If you had a black hole that was as massive as a sun, it wouldn't be as dim as the torch. You'd have to keep going dimmer and dimmer and dimmer from there by the same factor again. And that is the kind of level of stuff that's leaking back out of a black hole. So it's incredibly slow. It will take many, many times the age of the universe before a black hole actually appreciably shrinks due to leaking this material back out.
Can we use that material, though, and information intrinsic to it, to infer things about the black hole that released it, so it gives us an insight into what that black hole is doing and what it's eating?
The honest answer to that question is we don't know at the moment. It's something called the information paradox, and it's a subject of active research.
And maybe we'll find out what that is later on. Andrew Pontzen, thank you very much.
The Naked Scientists podcast is produced in association with Spitfire, cost-effective voice, internet and IP engineering services for UK businesses. Find out how Spitfire can empower your company at spitfire.co.uk.
This week on The Naked Scientist, we're paying tribute to one of the greatest scientists of our time. That's Stephen Hawking, who passed away on Wednesday the 14th of March in his home in Cambridge.
Due to his motor neurone disease, Stephen Hawking already had limited powers of speech, but then in 1985, when he contracted a near-lethal dose of pneumonia, a tracheotomy to save his life simultaneously robbed him of his remaining ability to speak. Yet his ability to communicate his science is undoubtedly one of his most outstanding characteristics, and this was made possible by the speech synthesizer system that ultimately became one of his most powerful trademarks. Lama Nachman is Director of Anticipatory Computing at Intel, who developed the most recent computer system that enabled Stephen Hawking to talk to the world, and she's with us. Hello, Lama. Welcome to the programme. Actually, how did Stephen Hawking use his first speech technology? How did it work?
Yeah, so after he lost his voice, he was actually using spelling cards for a while, where he would just essentially use his eyebrow to indicate yes and no. And then there was an early software that was done by a company called WordPlus, and the software was called Equalizer. And basically it allowed him with a joystick to select letters and complete words so that he can actually speak. With that, there was another piece of software, which is called Speech Plus, and that took the output from that first system and essentially spoke that out through that analog speech synthesizer. To date, this is the speech synthesizer that he's been using all along. And the reason for that is that he really associated that to be his voice. So all along with all the technologies and all the improvements, he continued to actually use that one piece of software for the actual speech synthesis part.
How did he control the system in the first place, and how did that have to evolve as his condition evolved?
Right. So initially, he was able to actually use his hand and control a joystick. However, in 2008, he couldn't do that anymore because his hands were not strong enough to do that. So his technical assistant at the time managed to cobble some different off-the-shelf actually components and build the sensor system that he actually attached to his glasses. And it's essentially an infrared sensor. So when you actually move, the sensor will actually detect that movement. So it's similar to what you would have today in phones, for example. When you bring your phone close to your ears, it will detect that there's something close to it. So
was this an eye movement? It was looking for him moving an eye or looking in a certain direction, or was it just detecting facial movement?
No, it was literally his cheek movement. So as he moved his cheek up, the sensor detected that movement and sent that signal, which was equivalent to essentially the pushing of a button. He just pushed the button with his cheek.
And what the system is then presenting possible things he might want to say, and he's selecting and slowly honing down on a list of things to build words, sentences, phrases, and so on.
Exactly. So imagine a keyboard, for example, where letters continue to get highlighted. And when the letter of interest is highlighted, he will move his cheek, it will select that letter and put it in. Now, there's word prediction, so he could select the word that he wants if that word shows up as he starts to type these letters. As he moved from that original system from WordPlus to something called Easy Keys, where it allowed him to control his whole Windows interface. So now imagine beyond just clicking a button, you can in the same way emulate something like a mouse movement. So you will scan the whole screen, and as you come closer to the row of interest, he will click, and then it will start going through the columns, and as it gets to the column of interest, he will click again, so he could select any point on his screen.
Now, you at Intel got involved about 5 years ago, so what was the step change that you brought to the party?
Right, so in 2011, he reached out to Intel, and basically his issue was that he couldn't really control his interface well anymore. Part of that was because it was very hard for him to move his cheek very reliably and trigger that sensor. And part of it was that the whole system was just old enough that as he had a hard time controlling the sensor, everything else essentially ended up being too slow. So we went out there and we tried to first understand what was needed to change. And through observing him for months and months and months, right, we thought, there are so many different things that we could actually do. There's gaze tracking, there's brain-computer interface, all of these revolutionary methods. And as we continued to look through these things, he continued to reject all of those. And some of those didn't work for him because, the gaze tracking couldn't actually lock on his gaze. The brain-computer interface couldn't get signals from his brain. And he actually joked that maybe he doesn't have any brain signals to actually be measured. But, through all of this, we realized that, he wasn't really looking for something that's revolutionary. He really wanted something that was familiar. So then we started to actually go back to the drawing board and try to understand how would we design the system that's more efficient, but still looked and felt the same. And I think that was pretty much the hardest part of what we had to really do.
You obviously triumphed because you kept him communicating.
Yes. it took a couple of years and a lot of failures. But then after that, I think we finally figured out how to keep the look and feel the same, but automate a lot of stuff that was actually being done by using the mouse and being done inefficiently. So if you imagine, for example, if somebody wants to open a file or something like that, it doesn't really make sense to think of this as a whole series of mouse clicks that take forever. Instead, you want to just automate that whole process under the hood and just give him a few options that he can select from. And that essentially was kind of the aha moment, right? Where we just looked through every single thing that he did with his machine and over time built a lot of automation under the hood to actually make that faster. The other part of it, which was typing and communicating, so just to speak to others, that part, word prediction brought in a huge improvement. So we were trying to really just reduce the number of clicks that he needs to make before actually the thing will predict what he's trying to do, and do that in a way that was cognizant of what he was trying to communicate. Because when he's trying to talk to people, it's very different than if he wants to type a document and do his research or search the web.
Lama, wonderful work that you did. What was it like working with Stephen Hawking? Was he a good customer?
It was phenomenal. It was probably, the most amazing thing to watch. I mean, he was a force of nature. He just persevered. He kept working and working on improving that system and giving us all the feedback that we needed to actually make that into something that he could actually use.
Wonderful. Thank you very much for sharing that story with us. That's Lama Nachman from Intel in San Francisco.
Now, Professor Hawking undeniably made huge contributions to science, but he's also done a lot for public understanding of science. Professor Jerry Gilmore, who's a cosmologist himself and also a powerful proponent of public engagement with science, is with us. Welcome, Jerry. So what would you say Hawking's contribution to the understanding of science was?
Well, the most important thing to note is that no one listening to this program doesn't already know who Stephen Hawking was. He was arguably the most famous person on the planet working in such esoteric subjects. That immediately breaks down the stereotype that scientists are old white men wearing white coats and normal people can't do anything like that. So that was probably the most famous and most significant thing of all. His book really took off. So it raised the whole profile of people thinking big questions and about really, really broad topics. And that is enormously important because the biggest impact that we as scientists can have is not to answer the questions, but to get real people in the real world asking questions themselves. So they look around them and say, why is it so? How did that happen? Where did it come from? And that not only stimulates young people to take up challenging careers. We still get undergraduate applications every year saying, I got stimulated by reading Stephen Hawking's book. And sometimes they even have. But the real thing is that if everybody starts questioning what they see, then we would not be in this silly situation where no one believes experts or where fake news is marauding the world. You can say, well, let me just stop and think. And just encouraging that, which he did spectacularly, is fundamentally necessary for society, and he deserves enormous respect and credit for his efforts in doing it.
And something I've noticed is that the best scientists in the world sometimes is completely unable to break down their work to something that someone from another field might be able to understand. So to have this skill to be able to break down such huge concepts, that's quite incredible.
You're right, it is rather rare. It's not as rare, perhaps, as some people think. You keep having excellent people on this program who do a great job of it. Popular science books are on the bestseller charts all the time. But nonetheless, some of the concepts you heard Andrew Thompson a minute ago trying to tell you what the inside of a black hole was all about. Some of those concepts are pretty intellectually challenging, and particularly when you get to the really basic properties of nature, general relativity, quantum mechanics, and so on. But the fact that it is even possible to think about these things is what's really interesting. Kids can dream.
And I fondly remember the episode of The Simpsons Stephen Hawking appeared in. He also appeared in Star Trek, The Big Bang Theory. He lent his voice to a Pink Floyd track. So what kind of effect do you think this would have had?
Well, this was the real key. This is the fact that you get out of the narrow niche of the people we normally talk to. Out there's a small subset of the community that listens to programs like this and thinks and reads. But then there's a whole huge world of people who are only vaguely aware that other worlds exist. And crossing those boundaries was something that his image took off. I mean, just look at the Paralympics as the power example. I mean, this year's Paralympics ended with a tribute to Stephen Hawking. Now, that's a whole new world and a whole different community globally who can suddenly realise, hey, it's actually socially acceptable to think about things and to ask questions.
Being a nerd is cool. And so has this brought more people into the field of physics, would you say?
Probably, but actually that's not so important anyway, to be honest. The world does need more physicists and more people studying technical subjects. But most of all, the world needs people who can stop and think.
Glad to have so many of you on the panel then. That's Professor Jerry Gilmore. Thank you very much.
Now, as Jerry mentioned there, in 1988, Stephen Hawking released what was to become his seminal science book, A Brief History of Time. It's actually sold millions of copies in a variety of different languages, but for many, it's remained on the bookshelf gathering dust, because many people admit they never made it beyond the first few pages. Well, if you're one of them, perhaps former Cambridge astrophysicist Dr. Matt Middleton, now at the University of Southampton, can come to the rescue with his synopsis of what the book is all about.
I can't possibly do the content nor impact of this famous book justice. A Brief History of Time was Professor Hawking's way of placing the wonders of the cosmos within reach of everyone with a curious mind. It has helped shape and inspire a generation of eager scientists, and I count myself amongst their number. But in any case, I'll try and break his famous book down by telling you about my favourite bits of the physics it explores. Here's a very brief history of A Brief History of Time. Stephen Hawking worked extensively on black holes, from the mind-bending nature of singularities to the establishment of black hole thermodynamics, before we even had any observational evidence that they existed. Now they're a mainstay of observational astronomy, from hot gas clouds pulled apart by supermassive black holes, to smaller black holes stripping material from a companion star. More recently, LIGO confirmed their presence from the detection of gravitational waves, as two spinning black holes collided and merged together. I'm sure Professor Hawking was also excited by the prospect that we might soon see a black hole for the first time. Telescopes all around the world are lining up to create the biggest telescope ever, the Event Horizon Telescope. The path of the light near a black hole is bent by gravity, resulting in a shadow that we can observe with this extremely high-resolution instrument. This gravitational light bending, the idea that the path of light can be affected by gravity, is presented in A Brief History of Time. It is a direct consequence of general relativity, which predicts that both the paths of light and matter are affected by massive objects. It is now used extensively in the discipline of lensing, where massive objects or collections of objects, such as clusters of galaxies, can bend light around them. When they intersect, they amplify light so we can detect and study very distant objects. The study of distant objects connects rather nicely to other themes in A Brief History of Time, notably the expansion of the universe. By looking at how light from distant galaxies is shifted compared to light you might see in a laboratory, Edwin Hubble famously confirmed that galaxies were, almost exclusively, retreating from us. A notable exception is Andromeda, which will collide with the Milky Way in a scant 4 billion years. The realization that the universe is expanding remains one of the most important in human history. Extrapolating backwards inevitably results in a point in time where all the universe's mass was contained in an extremely small space. The explosion of space and time from which the universe emerged was dubbed the Big Bang. Stephen Hawking worked extensively on this concept, and naturally it features heavily in A Brief History of Time. When we look at the residual light and radiation from the Big Bang, known as the cosmic microwave background, the fluctuations are so extremely small in any direction that we look, we know that the universe was once incredibly compact and expanded very, very quickly. When I say quickly, we can work out it expanded in 100 millionth of a trillionth of a second by a factor of 10 to the power 50, a number so large I don't even have time to say it. In fact, this inflation was faster than the speed of light. But don't panic, the expansion of the universe doesn't have to obey the speed of light. We think this inflation is down to something mysterious called vacuum energy, also called dark energy or quintessence. One of the things I really love about A Brief History of Time is that it's about more than just the science. It's also a story of development and our place in this beautiful cosmos. Stephen Hawking presents a human perspective throughout, navigating our movement away from a Ptolemaic view of the universe, where the Earth was at the centre, through the Copernican revolution of a heliocentric solar system, and to the point where we do not inhabit a special place in the universe at all. Whilst this may sound a tad bleak, we should take comfort in the fact that the universe may have been just right for life to develop, referred to as the anthropic principle. If the universe wasn't able to support life, then we may not have had the stars and galaxies. Mankind may never have dragged itself from the primordial swamp, and, most upsettingly of all, the universe may have been denied minds such as Stephen Hawking's, and we may not have had a brief history of time at all.
Thank you very much to Matt Middleton from the University of Southampton with a brief history of time. I alluded to this earlier, Andrew, and that was that you ended up as a contributor to the appendices of Brief History of Time. Now, that's quite an accolade.
Thank you. Because it's a very boring story in a way. You know, I got an email and then did it. So, I mean, a slightly more interesting...
I'm recording all of this and it's intriguing. So you get an email, from Stephen Hawking, says, will you write my book for me?
No, it was from the publishers, I'm afraid. The situation was that they wanted to do an update to Stephen Hawking's Brief History of Time. And of course, Stephen Hawking wanted them to do an update as well. But he was an incredibly busy person. And writing is something that clearly in his later years was quite a time-consuming process. So the process that we went through was essentially one of drafts and then getting feedback on the drafts and going through a sort of iterative process to come up with these appendices.
As a physicist, having your name in A Brief History of Time, surely a massive temptation to show everyone all the time at parties?
I have to say it's not like a co-authorship. I think it's quite clear who's in the driving seat in that particular collaboration. But my name is in the acknowledgements, so I'll take that.
If it was me, I'd be getting it out all the time. Look at what I did.
Yeah, but you have to turn to the acknowledgements page, so it's sort of it's a bit too fussy.
Andrew, we're impressed, and that's what counts here. Thank you very much, Andrew Pontzen from UCL.
Hawking's scientific contributions remained of great interest to the world, and this was demonstrated when the university library released his PhD thesis online for free. In fact, it was so popular the website crashed. I went to visit the Cambridge University Library to take a look at the thesis itself and find out more about the most downloaded PhD of all time.
Well, I'm Dr. Arthur Smith. I'm the Deputy Head of Scholarly Communication at the University of Cambridge, and this is Professor Hawking's PhD thesis, Properties of Expanding Universes. It's actually, I think, his copy of his thesis as well.
Oh, wow. So, introduction, the idea that the universe is expanding is of recent origin. We could just sit here and read his PhD if we wanted.
Yeah, I think you could probably get through the introduction, but then by the time you get to a couple of the other chapters, you might struggle a bit.
Oh, wow. And here's some handwritten equations that I couldn't begin to comprehend.
No, well, I mean, this thesis obviously predates a lot of computers, so it's all typewriter, and then a lot of the equations and then a lot of the symbols and notations are all done in his own hand.
Have you ever read it?
I have skimmed it.
Is it possible to skim?
Well, maybe not. I think there is certainly a lot of knowledge contained in this thesis, and to get a full appreciation for it is probably going to take some people probably a lifetime.
And for others, including myself, that's probably not long enough. Why do we have a copy of the thesis here?
I mean, as part of all PhD theses, all students are asked to submit a copy of their thesis. So the university library has a copy of his thesis, and we've held that copy ever since he submitted it in 1966. It wasn't until recently, though, that it was digitised. At the time, what people could do is you could ask the library for a copy of the thesis if you wanted it, and the library would digitise the thesis and charge you for that privilege. So his thesis was first digitised by request in about 2013. In about 2015, when the Office of Scholarly Communication got started up, we did a big push to make a lot of the old PhD theses from the university available online. So that first happened in 2015.
Right, and then when did it become publicly available?
So we did a lot of work in last year, 2017, working with Professor Hawking and his team to get permission to do this. And so we made it available in Open Access Week, which happens every year, which celebrates open access to research publications. So that happened in late October 2017.
Right, and then it's sort of the floodgates opened, I suppose.
Yes, the floodgates, well, the dam burst, I think is the better expression. When we released his thesis, we got a huge amount of interest. Within a couple of minutes, we'd had thousands of downloads. People are hugely interested in this work.
How many do we know in total who have read this?
Well, I don't know how many people have read it. That's a
different question.
That's a more difficult question. But we think about 1 to 2 million people have downloaded the thesis.
That's incredible, and that's more than any other thesis.
Oh, absolutely. It's almost more than the rest of all the items that we have in our open access repository combined.
Do you know if this is all physics students from around the world, or is it more just the general population?
No, I think this covers everybody. We've seen downloads from, I think, every country on Earth, covering all spectrums. I think the interest in this thesis goes beyond just the physics community. It spans all sorts of people in the world.
I do feel quite privileged to be looking at it in this form, with all these handwritten equations and full of cosmological solutions. So I suppose that's why people want to read it. It sort of promises a glimpse into how the universe works.
Yeah, I mean, I think everyone's interested in where we've come from and where we're going in some sense. And some of those answers, well, attempts at answers at least, are in this thesis and really sets the groundwork for what Professor Hawking's work was going to be for the rest of his life.
Are there any photos in it?
I don't think there are any photos.
It's not a picture book.
Maybe there's a photograph in here of the universe before it began, but that's a bit of a stretch.
No photos, but still a very interesting read, I'm sure. That was Arthur Smith at Cambridge University's library.
We've discussed Stephen Hawking's earliest work, including his eponymous Hawking radiation, but his exploration of our puzzling cosmos didn't stop with that work. He continued exploring the workings of the universe throughout his life. Claudia de Rham is a theoretical physicist at Imperial College in London. Now, Claudia, Andrew Pontzen has sort of craftily, earlier in the programme, set you up in the sense that he made a reference to the information paradox, and we said we would cover this later. Over to you. Take up the baton and tell us what this is and why it's relevant to Stephen Hawking.
So, as Andrew mentioned, one of Hawking's biggest discoveries is the fact that black hole can radiate, and so they can evaporate, they can lose energy over time. That means that if black hole evaporate, after a finite time, they just disappear. There's no more black hole there. And that's really led to one of the biggest paradox in physics, which is the information loss paradox. Because the information that leaks out through this Hawking radiation is minimal.
Can you just define what you mean by information?
So when you have a black hole, stuff may fall into the black hole. There may be stars, there may be other planets, there may be a whole civilization. And so they encode information. Just like a book encodes information, we have information about just what's going on in the star. Just think of it of knowledge. There's some knowledge there.
It's like order. So in a disordered universe, you're feeding material into a black hole that's ordered and organised in a certain way,
that's right.
Whatever that way is.
That's
so
right.
It is ingesting order.
It is ingested order, but really think of it of some type of knowledge that you send into the black hole. Now, if you have an everyday, your everyday life, when you have information, it gets moved around, it may change state, but information remains conserved. So if you take a book, this is one of Hawking's famous analogy. If you took a book and burnt it, the information of all the words that were written in the book is still there. You're going to need to work extremely hard to retrieve it. So you need to analyze all the fumes and the temperature and the ashes, but ultimately it's still there. The information is conserved. It may be harder to get access to, but it's still there.
So what's the problem with the black hole then?
While the black hole is still there, you may think, well, the information is stored inside the black hole. Maybe you don't have access to it, but as physicists, it makes us happy because we know, hey, here's where the information is stored. But now if the black hole is able to evaporate and entirely disappear, then where is the information gone? That's one of the biggest paradoxes. And it's not only philosophical. It's not just like we like to conserve information. Is that from a quantum mechanical point of view, the information should be there. So where is it?
So something's missing. Is there something missing from our understanding of how a black hole works? Is that information leaking out of the black hole in some other way? Or is something else happening to the information to balance this equation and we're missing a term somewhere? What do people like you speculate may account for this?
Exactly. Well, you should be a theoretical physicist. These are exactly the questions people are asking themselves. And the answer is we don't know. This is still an open question. But Hawking himself, throughout his career, tried to come up with different possibilities. So when when I was finishing my PhD in 2005, he had a revolutionary paper. He thought he possibly had an answer to that. And in that, you had to consider new configurations. So he was using some of the framework he's been working on earlier in his career of quantum gravity, where you have to sum over all possible geometries, if you want, according to the laws of quantum mechanics. And while the dominant ones may seem to be losing information, maybe you need to take into account other ones for which, and when you sum over all of them, all the information would be restored. This was one possibility, but the community as a whole wasn't necessarily entirely convinced, and then later on himself may not have been convinced by that.
So in a nutshell, what can we learn from what Stephen Hawking has laid as the foundation that people like you are now working on?
Throughout his career, he won several times in trying to find different ways to tackle this problem, find different resolutions, and he was never entirely satisfied. I think this is a tremendous legacy for how research can be done. He really had physics at heart, well above his ego. He really wanted to get to the bottom of the questions, and even if he thought he may have had a solution originally, he kept going on to try to understand what the real resolution could be.
He was certainly motivated to have perseverance, wasn't he?
Exactly.
Certainly sure.
Yeah.
Claudia Durand, thank you very much indeed. Well, we're very lucky to have assembled some very fine minds here in the studio who have been helping us to reflect on the work and the life of Stephen Hawking. Could I ask you, Martin Rees, for any additional thoughts or your reflections?
Well, I first met Stephen Hawking in 1964 when he was just diagnosed with his disease and wasn't expected to live more than 2 years. And I'm an astronomer used to large numbers, but few are as large as the odds I'd have given then against him surviving another 50-plus years. And mere survival would have been marvellous, but in fact he did more than that. He became the most famous scientist in the world. An amazing achievement.
Jerry Gilmore?
Well, Stephen holds the world record for the number of wheelchair bangs to my toes.
So it's his tree did used to drive over people's feet?
Well, yes, it was in applied maths. Old building, narrow corridors, and he always came in just as I was finished a lecture course and always managed to hit my toes. But continuing on the earlier theme, I think it is his inspiration that he has managed to provide beyond subjects that is really the remarkable legacy. I mean, he is a global figure.
Also with us is Andrew Pontzen. What are your thoughts?
I think he really encapsulated a kind of freedom of thought. And I think it sounds slightly strange to say this, but even amongst theoretical physicists, there's a danger that people get stuck in a rut and work on one thing for their entire career. Something that Stephen Hawking showed very clearly is that it's possible to actually jump around and think about many different things and not be afraid of the traditional boundaries. And there are relatively few people who really show that to us. In fact, very sadly, astronomy lost another individual that in my mind is a bit like this, Donald Lyndon Bell. But to my mind, those two people were the two people that really showed me that actually you can be very adventurous and play around with what's possible.
True for you too, Claudia?
Absolutely, yeah. I think the more I went into my research, the more I realized how, well, as I said before already, how true to himself he was. And also you realize how deeply original his way of thinking was. There's and now you see it in research. You can see some different people in research and you say, oh, wow, that's a little seed of Stephen Hawking. You can see it just there. It's amazing how he has really seeded some of his extremely original way of thinking into the community. It's an incredible legacy.
And Martin Rees, you can always judge a good scientist by how many big problems they leave behind unsolved for the next generation. True of Stephen Hawking, of course?
Definitely. And what's amazing is he kept going. Many theoretical scientists lose momentum, but he kept going. And indeed, his last paper, written with a collaborator, Thomas Hertog, a Belgian professor who was a former student, is in press at the moment. So he kept going, and this is a paper on the multiverse and very technical, so it's wonderful he's got this more than 50 years of sustained contributions despite all the odds.
Well, thank you everyone who helped celebrate Stephen Hawking's work and life with us here today. You've been hearing from Martin Rees, Andrew Pontzen, Claudia Durand, Jerry Gilmore, Lama Nachman, Jameen Sridharan and Matt Middleton.
Now, it's clear that Stephen Hawking has had a huge impact, not just on the scientific community, but across the world. He supported science communication, he supported the motor neurone disease cause, he was a staunch supporter of the NHS and used his popularity to raise awareness for both political and environmental problems.
Many people took to social media this week to express their love and respect for Stephen Hawking, so we're going to end the programme by sharing some of them with you.
A few months ago, I was hunched behind Stephen Hawking's chair trying to fix a loose connection that was stopping him speaking. I found it and asked him if he could speak now. No, he replied, with a cheeky grin. He'll be greatly missed.
My name is Brendan Owens, and I'm an astronomer at the Royal Observatory Greenwich. For me, Stephen Hawking was a legendary scientist who seemed larger than life. In my mind, I always put him up there with Albert Einstein and Isaac Newton, which might sound fitting given his genius, but really what's running through my mind is when he guest starred on Star Trek at a poker game on the holodeck with Data, Newton and Einstein. If ever there was someone who encouraged a zest for life and a passion for science despite the challenges life dealt, it was Professor Stephen Hawking.
When asked about his illness, Hawking once responded, "It's a waste of time to be angry about my disability. One has to get on with life, and I haven't done badly." Stephen Hawking's achievements are testimony to the resilience of the human spirit in the face of adversity. His indomitable nature drove him to academic excellence. He was well known for being willful, yet his legacy, in so many ways, is unparalleled.
My name's Sheena Cruikshank. I'm an immunologist at the University of Manchester. When I was a student, I read Stephen Hawking's A Brief History of Time because I really wanted to broaden my knowledge of science. It really brought the fundamental ideas on physics to life for me, and it was an incredible inspiration. My only regret is that I hadn't read it earlier, as it would have been so useful when I was studying. He was such a great mind, and he was a real role model.
I'm a wheelchair user, and I studied law at Cambridge in the 90s. I regularly raised Stephen Hawking when I saw him out on the street. I never told him that's what I was doing, so unsurprisingly, I went all the time. I was also mistaken for him once. I'd gone to see one of his talks and arrived at the lecture theatre just in time. I was let in through the wheelchair entrance, not realising this led out onto the stage. The moment I appeared on the stage, the audience went completely quiet. It was only when I turned to face the front that the pennies seemed to drop. A few minutes later, Stephen Hawking himself appeared, an amazing man.
My name is Jessie Parrott. I'm a third-year PhD student with cerebral palsy and a wheelchair user. I've said this many times before, but as a disabled kid who wanted to go to university and wasn't sure if I could, Stephen Hawking was a shining light of hope. He inspired me not only to do an undergrad degree, but to keep going to PhD level. Thank you, sir, and RIP.
My name is Tasabi Mohammed, and I'm currently doing my PhD. And despite that being in genetics and not physics, Professor Stephen Hawking has been beyond an inspiration or a role model to me in my scientific career. He advocated for curiosity and for love for science, which are crucial in something as grueling and mentally challenging as a PhD. The world has lost a truly unforgettable genius and a beautiful mind. May his soul rest in eternal peace.